Thanks a lot. Can you see my presentation?
Yes.
Okay, so I go ahead.
So
Good morning. So today I'm gonna briefly introduce indium arsenide quantum dots and our work at IIT on this kind of dots in the framework of IEMAP. So before speaking directly about indium arsenide quantum dots, I would like briefly to introduce infrared quantum dots in general, as these compounds can be employed in future photovoltaic applications as absorbers or in solar concentrators that you can see here. And in this case, they behave as absorbers and emitters. They can be used as probes in bioimaging applications where organic tissues are transparent, enabling this kind of very high resolution imaging of even living bodies. And they can be used in optical communication or even in light emitting diodes and photodetectors. And these last two, if combined together, can be used in other, I would say, emerging applications like night vision cameras or cloud or fog vision cameras. And for many other purposes, like for object inspection, medical inspection, and I would say food inspection. And in details, these dots have the power to lower the costs of all these devices, making them allowed for the consumer market. Why? Because currently all these devices are made with materials obtained with epitaxial techniques, which are, for example, molecular beam epitaxy or these things, which are very costly, and even the process of making the device is very costly. While these colloidal quantum dots can be made as inks, so with wet chemical approaches, which are cheap, and they can be integrated in CMOS technology, which is readily available. So going into the details of the materials working in the infrared, as you can see from this graph, most of them are lead and mercury-based chalcogenides, and the synthesis of these compounds is now well developed. It's possible to govern their size distribution, and therefore the optical properties, the surface that have been implemented in devices. But the main problem of these materials, as you can see from their composition, is that they are toxic. So they are not the best option to go for the consumer market. So one of the best alternatives are indium arsenide quantum dots because they are compliant with the European directives. And every time we speak about this indium arsenide, people are concerned about the toxicity of arsenides, which are not well known to be non-toxic. But if you carefully look at the European restrictions, metal arsenide shall not be employed for any application related to water. So application, for example, fishing or fish farming or boats, water treatment devices, and they are not neither allowed for preservation of wood. So every kind of wood in which you use metal arsenides in the painting, for example, it's really not allowed because then it's exposed to rain or water, and then metal arsenides go into water. On the other hand, there is no restriction on the consumer electronic market, so we can go ahead and use indium arsenide in this field. So as regarding the synthesis, the first synthesis approach reported in the 90s is based on this molecule, which is trimethylsilyl-arsine. And after, I would say, more than 20 years now, the synthesis of indium arsenide with this precursor is quite well developed, still not completely developed. But the problem is that this precursor is very expensive, is pyrophoric, so it's very hard to handle, and it's not neither easy to purchase. So indium arsenide dots made with this compound maybe are not the best option to go to consumer market. So people looked for different alternatives, and the best one so far is this molecule, which is called aminorcine. through which nowadays is possible to make indium arsenide quantum dots. And the clear advantage of this molecule is that it's very easy to handle, is cheap, and it's very also easy to find on the market. So what's next? What we are doing now is to improve the control over the size and size distribution of these indium arsenide nanocrystals made with this cheap molecule. Why? Because if you get high control over this property, that is the size and size distribution, you can go for efficient photodetectors. A second goal is to enhance the photoluminescence emission of these dots, because if you make these dots very emissive, then you can get very efficient LEDs. So as regarding the first point, in the IEMAP framework, what we did in a first work, published a couple of years ago, we tried to improve the size distribution by employing zinc as an additive. Here you can see the absorption curves and the PL curves of the samples we made. From the absorption curves, what we can retrieve is the quality of the sample. That is, if the size distribution is narrow, this absorption curve is narrow. So we can judge this absorption curve to understand if our synthesis was good in terms of size distribution. And if I plot here this width, what you can see is that by increasing the amount of zinc, indeed, we could improve the control over the size distribution. In yet another work, what we did was to combine the typical ligand employed in this synthesis, which is a primary amine, with the tertiary amine that you can see here. And the combination of the two led to these kind of samples. As you can see, the absorption peak is a bit shifted, meaning that the size is not exactly the same. These are larger than this. And again, if I judge the width of these curves, what I can see is that employing the combination of the two ligands, again, we got an improvement in terms of size distribution control. So most of our efforts were devoted to the second point, which is to enhance the photoluminescence efficiency of indium arsenide quantum dots. And what people typically do to enhance the PL of these indium arsenide dots, or in general to semiconductor quantum dots, is to passivate the surface with the shell material. So typically what we do is to cover indium arsenide or other dots with a shell material that is able to passivate the surface defects and to confine the exciton, meaning boosting the recombination of excitons in the core region, eventually getting what we call core shell materials that you see here. If I now check the shell materials that I can use to cover indium arsenide, these are the most common ones. And if I exclude cadmium for toxic reasons, you can see that the choice is quite limited, and the lattice mismatch expressed here as a percentage is typically quite high, especially from indium arsenide zinc selenide. And indeed, people reporting this kind of heterostructure so far got very, not very, but quite low quantum yield, that is the efficiency of the system. Why? Because there is a quite high lattice mismatch. So in the IEMAP framework, what we tried to do was to improve the efficiency of these systems, employing our new synthesis approach based on the addition of this zinc. So here you see the schematic picture of our synthesis approach. And with that, we got first indium arsenide quantum dots, and then we grew a thicker and thicker shell from one monolayer, so like one layer of zinc selenide, up to 7 monolayers of zinc selenide. So if we check now the TM picture of these dots, you can see that they are relatively small at the very beginning of the synthesis. This is just pure indium arsenide. And then we grew the shell larger and larger. So you can see that the size increases by the overgrowth of our shell material. And if we now check the optical properties, you can see that our dots absorb more or less at 800 something, 900, and they emit at 950 nanometers. So they emit in the near infrared region. And if we check the quantum yield, the efficiency of this emission, you can see that we reached values as high as 70%, which is extremely higher than the 10-15% reported so far. So we got a record value. And this record value is not really compatible with the high lattice mismatch between these two materials. So we were kind of surprised about this. And these high quantum yield indicate that there should be something which we can call a magic layer in between the core and the shell, allowing for the stress to be reduced by the two. So we investigated the nature of this layer. We first perform high resolution TM. Here you can see a single core shell structure in which the core is made of indium arsenide, as you can see from the color code, and the shell is zinc selenide. If we go to higher resolution, here you can even count the atomic columns, and you can count the number of planes here. So you can count the thickness of the shell and the size of the core. And moreover, you can even judge how these lattice parameters vary along one single nanostructure. And here you can see that the core has lattice parameter compatible with indium arsenide, and the shell lattice parameter compatible with zinc selenide, meaning that there is no strain in this structure. And to investigate why there is actually no strain in this structure, we performed calculations coupled with empirical analysis. And what we found is that the reason why we don't have such stress in our structure is that because in our conditions, we are forming this interlayer, having lattice parameter in between these of the shell and these of the core. And so this is the, say, magic layer capable of making this structure so bright emissive. In yet another work, we tried another different interlayer, not indium zinc selenide anymore. We tried indium phosphide because it features lower lattice mismatch with indium arsenide, as you can see from this sketch. And we devised a synthesis approach, again with the cheap amino acid molecule, and we coupled it with another very close molecule, which is called aminophosphine, to grow the phosphine shell. Why? To make everything cheap. And as you can see from the sketch and TM images, what we got were indium arsenide, indium phosphide core shell structures in which the indium phosphide shell didn't grow exactly isotropically, but grew also a bit faster on the vertices of the starting indium arsenide, forming this fancy core shell structure, which can be also called tetrapod because of the 4 pods that you can see in the sketch. We covered them with a zinc selenide shell to form these complex heterostructures, and eventually we got a bright emissive core shell structure in this case, with emission down to 1000 nanometer. So we were the first having such bright emission with these amino arsine and aminophosphine based compounds. So eventually, as we are aiming at devices, we employed our indium arsenide zinc selenide dots in real application like LED. This is the structure of the LED. This is schematic representation of the LED. And we achieved initially an external quantum efficiency. So this is the efficiency of the device of 5%, which represented the first demonstration of a IR emitting LED based on this kind of quantum dots. And in a later work, we optimized the architecture structure of the LED. This is the final architecture we employed. And through this, and employing by our dots with high efficiency, we got a record value even in the LED with an external quantum efficiency of 13%. So with this, I'm done with the presentation. I would like to thank you for your attention, and I would like to thank all the people involved in all these works. Thank you.
Thank you, Luca, for your interesting presentation. And now we'll open the floor for questions. So there aren't any questions. Then move on with the following presentation from Stefano Toso, from the same institution, Istituto Italiano di Tecnologia. And Stefano,
hi.
Good morning. The floor is yours.
So let's try.
Can you share your presentation?
Yep. Do you see my screen?
Yes. Yes,
okay.
We see.
So I guess let's go.
Thank you.
Okay,
Thank
so
you.
indeed I am from the same group as Luca, from the same institute. Actually, I finished recently a successful postdoc there under the IEMAP framework, and they moved like last month, but I'm still very fresh on the topic. And this talk today is gonna be half and half, let's say, into modeling of materials and somehow also into making, but more on the modeling. We're going to talk about how to design epitaxial nanomaterials, which for us it's a quite new and exciting direction. So I want to start easy and make sure that everyone is on the same page. When we go into functional materials, you can do a lot of stuff by using one material alone, right? One good example is glass, that is one material that can do a lot of things. But in reality, and especially in more modern technology, most times you want to put materials together because you can harvest the properties of both, right? These are simple examples of like mechanical properties where you have rebar in concrete or carbon fiber, and they're both great materials, right? The problem is that when you want to make composite materials and you want to exploit the property of both halves, you need to make sure that these materials talk properly, right? Because again, for example, in rebar, if you don't match the thermal expansion, your building will crack. In carbon fiber, if the resin doesn't adhere well to your fiber, it will delaminate. And you have a similar problem in electronics. That is where actually the talk will go. We are going into this direction, right? In electronics, very rarely you use one single material, but you will have a complex architecture made of more or less similar materials together. Like this is an example architecture for a blue LED. And these materials have to crosstalk in a proper manner. You cannot just glue them together, right? So that's where the challenge is. And you need to make sure that at the interface, these materials will touch properly. Because if you have something bad, like on the top right image that I'm showing of a random interface, your device will simply not work. And this is good part of the reason why making blue LED was so difficult, for example, and they got the Nobel Prize in 2014, right? So the trick behind gluing materials for electronic applications is epitaxy, and I'm sure that most of you are very familiar already with the topic. Actually, Luca was bringing it up before, but for this talk, it's important that we go a tiny bit more in detail. So what you do in epitaxy is that you have one material and you grow on the top another one that matches more or less exactly the crystal lattice, right? Indeed, the word comes from the Greek epitaxis, that means above and in an ordered manner. This is an ideal situation. Of course, in real life, you almost never have it. But you can have some, for example, strained interface where one of the two materials can adapt to the other to some extent, right? And if you really don't manage to, at that point, you start having defects, right? And this is where the problem comes, because in an ideal ordered interface, like the one on the left, you have no defects whatsoever, or like the concentration of defects is very limited. Your electronic properties, your optical properties, whatever property you want actually from your material, provided that electrons are involved, it will be fine. It will be optimal in a way. But then, if you start having defects at the interface, like the ones shown here, and you don't even need to have so many, you need a tiny bit, you start having a disruption of your properties, right? So one important thing is to understand when two materials can be glued together in this manner in a proper fashion. Usually when you talk about epitaxy, the distinction is between homo and heteroepitaxy, right? Homoepitaxy is one material on itself, for example, gallium nitride on gallium nitride doped. And heteroepitaxy is basically two different materials put together. But in reality, I find that this distinction is not as useful as another one, that is the one between isostructural epitaxy and heterostructural epitaxy. So in isostructural epitaxy, or what I call so, I don't know if it's an official name, but it works, I think. In isostructural epitaxy, you have two materials that are similar. They are not the same, but they are similar. They have the same crystal structure, they have the same space group, the same symmetries. The atoms can change. So these are the examples. Some examples already Luca showed before, but these are other examples, right? So indium phosphide on gallium arsenide, these are oxide perovskite, cadmium sulfide on cadmium selenide. These are not the same materials, but if you go and check their crystal structure, they are very, very similar. Or you have another case that I call non-isostructural epitaxy, where you have two completely different materials that share no similarity on the structural level, but that accidentally, or more or less accidentally, they do fit with each other. And this is the direction we want to go into. I'll explain you why in a second. So two examples are of these two epitaxies are the quantum dots, the contra-shell quantum dots that I'm sure you're familiar with. They won the Nobel Prize in Chemistry last year. Luca was showing them, so I mean, it's not nothing new, right? But here, epitaxy is important because it allows you to engineer the band structure, right? This is a case, a typical case of isostructural epitaxy, because the materials that you put together do have the same crystal structure. And this makes it quite simple to design such systems. A case that is more interesting for the direction I want to investigate, and I indeed investigated under the IEMAP framework, is the case of non-isostructural. For example, this is an example from literature where gold, the plasmonic gold particles were coupled with a semiconductor, I believe it was cadmium selenide, to construct hybrid semiconductor metal heterojunctions for photocatalysis, which is, again, related to energy applications, right? So these systems are interesting because you are less limited, right? You can put together materials that have drastically different properties compared to the case on the left, but of course you have challenges. The challenge is on the design, because if you try to design an isostructural interface, basically the only thing you have to care about is strain, right? And again, we heard about it before. These are few examples of typical strains reported in nanocrystals. But you are reasonably sure that if you can handle the strain, or if the strain is not too large, you're going to make it. Maybe you need to put a buffer layer to release it. Maybe it's not going to be so easy to find the growth conditions, but you might make it, right? The problem comes when you want to put together two different materials, and these materials can be very different from each other. Like on the left, again, cadmium selenide, on the right, gold. If you look at them visually, there is no simple way to figure out if they will like each other, right? And here come two questions. One is at the experiment design stage. I want to make this structure, and I have to ask myself, like, how can I make it? Do I have a realistic possibility to make it? Because I don't know if these materials will like each other. When I make this interface, will it be stable? And especially, are there other options that might pop up and I didn't think about during my synthesis? Maybe I'm targeting a certain interface, but another one ends up forming. And there are even more challenges, if you want, when you actually make the interface, because maybe you think that you have done a certain interface, but you have done another one. Or you think that your interface is epitaxial, but in reality, maybe you have a strong defectivity at the interface, or it's even amorphous. Maybe you didn't control properly the direction. This is less relevant if you are working in a thin film kind of configuration, but for us who work in colloidal nanocrystals, it's really difficult to decide where the two materials will attach to each other, right? It's not so trivial. And of course, you want to know a model of the interface to be able to characterize it and study its property, maybe simulate its properties. So here is a realistic example that came up in our group a few years ago, where we were targeting an interface and we ended up having this kind of issues. So the interface that we wanted was between two semiconductors, cesium lead bromide, wide gap, but like visible range semiconductor direct gap, and lead sulfide, the typical infrared semiconductor, right? If you have a look, the structures are different, but they are reasonably similar. Both materials are cubic, they both contain lead, the lattice constants are quite comparable. So what we were trying to do was to do an heterostructure between these two materials, right? We approach the problem colloidally, and what we end up having is actually heterostructures. But when we go in and check which materials we got, we didn't get lead sulfide. We got something else that we didn't expect. By the way, we eventually managed to make these heterostructures, not me, but colleagues in the group. The work came out, like, I think 2 days ago. So kudos to them. It was a challenging project, and I think we are all very happy to see it finalized. But okay, back to this specific problem that is back to 3 years ago. We did get some heterostructures. The material was not the one expected. But when we went into the characterization and studied the interface, we sort of figured out why it was forming. I mean, if you have a look at the structure on the right, you do see that the two materials match really well. They also contain the same atoms. Basically, you have lead, you have bromine. Okay, there is sulfur here, there is cesium here, but there are clear similarities that do allow these two materials to grow epitaxially. The problem is that we didn't know. And if we knew, maybe we would have designed the experiment in a different way. So this triggered the development that now I want to show you. What we did was we teamed up with a group of theoreticians from the Carnegie Mellon University in the United States who are active in the design and programming of codes for epitaxy predictions. Their library is called OGRE. And we teamed up to design a new framework based on OGRE that simplifies this job and is more oriented towards colloidal nanomaterials. And this is how it works. So the first thing that you have to do is to check the directions, the lattice directions in which the two materials like each other. After you have identified one or two promising options, you can prepare possible models of this interface. And what's next is that you actually optimize these models of the interface to find the best possible configuration, attribute a structure to the interface, and attribute an energy ranking, right? So you can also have an idea whether the interface will be stable or not. And we wanted this system to be really accessible to everyone and to be fast, because if it's a fast system on a small scale, then you have the potential to scale it up very efficiently, for example, using large computing infrastructures and access to crystal structure databases. So let's go a bit deeper into how it works. In the lattice matching step, here is we have a representation, a bidimensional representation. You have two unit cells of the materials, and you have to find a way to attach them to each other. One possible way is this one, and you have you see a periodicity at the interface that describes how the two materials crosstalk. But this is not unique. You have another one here where you tilted the orange material by, I don't know, some degrees, and then you have a similar periodicity at the interface, but of course the directions are different. Then you have this one where you tilted the cyan material by 90 degrees, and you do change the periodicity at the interface. And then you have this one that is a bit more messy. And in fact, if you carefully look at the corners, let's see if I can point. If you carefully look at the corners here, you don't have a great match. This is the strain that we were talking about. You still have a periodicity, but it is strained, right? Now, when you move it to a real three-dimensional problem, the same situation occurs. You have a base material that in our case, in our example, is the perovskite, and your other semiconductor that is, we call a chalco halide. You can attach it in different directions that are identified by Miller indexes. Again, you have to find how these two materials will match. At this point, we are in a bidimensional situation. So these are actually the surfaces of the two materials. And you have to find a situation where the same symmetry operations will describe properly both materials. If you manage, then you have an epitaxial match. Now, this situation is described and it's automatically identified by our code, actually. And it is described with this kind of tables where you see the lattice, the 2D lattices of one material, the 2D lattice of the second material, and the supercell. You can have, of course, many, as I was mentioning, but this would be difficult to read for a user, right? So what we do is actually we extract the relevant information from these schematics, which are the strain and the supercell area, and we condensate them into a matrix that it's easy to see. So given one direction for the base material, you can read how well the other material will match on that direction with its own facet. The circles identify the properties of the interface. So the more red, the more the strain, and you are not happy about it, so you want something blue. And the bigger the supercell area, also in general, the worse the interface will come out. So you want to focus on something that is small and blue. In this case, the green interface here, 100010, is the one that we experimentally found, and it was visibly promising from the metrics. But this is not nearly enough, right? You want to know the structure of a material. So what you do next is that you take your two compounds. You already know the relative orientation, so this is not taken by chance. You know it. And what you do is that you start cutting them at all the possible surface terminations. You create basically pieces of your puzzle, right? This material is simple. It can be cut at two levels, the lead bromide level and the cesium bromide level. This material is more complicated. You have 7 possible cuts. And what you do next is that you shuffle these possibilities to construct all possible interfaces for this set of terminations. You have 14 cases in this case. These are not even many. I mean, they can easily grow to 30 or more. And then you have to rank these situations, right? Because one of them will for sure be better than the others, and it will be the favorable one. How you do it? You take the two fragments of your model, and you try to optimize their relative position. You move them on the side, you move them top and down, and for each position, you construct an energy map. This energy map, in most situations, in most softwares, is computed by DFT, like density functional theory. That is something quite heavy to compute. And this is a limiting factor for us because we want to be able, first, for users to access this very quickly, potentially on a laptop. And second, we want to scale it up to access the database level, right? So this is the next step of the project. Of course, yeah, sorry, the energy map is bidimensional, right? So this represents the lateral shift of the two fragments, and this is basically the bonding distance at the interface where you have a minimum. So here what we did was that we implemented a Coulomb potential. It's a classical electrostatic potential, leveraging on the fact that most semiconductors that we work on in colloidal systems, and this is it's important to remind, are actually ionic compounds or partially ionic compounds like cadmium selenide, cesium lead bromide. They have a strong ionic component to the bonds. So they are acceptably approximated by an electrostatic potential. And the electrostatic potential that we developed is able basically to describe the same kind of curve by using a Coulomb term that is attractive or repulsive depending on what is on the surface, basically, plus a Born repulsion term that describes basically the situation where the two atoms are too close to each other and they start repelling due to the electron clouds, right? Now, these two terms together, if correctly parameterized, basically allow to reproduce quite well the DFT map and also the DFT potential energy surface minimum at a very small fraction of the computational cost. Indeed, all the simulations that I'm going to show you now are performed on my very laptop. So, and it takes like, I don't know, 2 or 3 minutes per interface. So they're really, really, really fast. When you use this potential, what you get out? You get out several evaluations, basically, for all possible interfaces. And you get, and that's what we care about the most, an optimized structure for the interface. So here we have 3 possible candidates. They all connect very well. So, okay, they are reasonable. But we also get an energy ranking, because now we know, for example, that this interface, energy-wise, is better than the other 2. And when you go and check the experiment, so you actually take the particle, put it under an electron microscope and check what's going on at the interface, you find out that our prediction is accurate. So the experimental structure is actually exactly not only the predicted option, but it also has the predicted geometry, which is quite an achievement. Another interesting case that was also financed under the IEMAP framework is this situation where we have a perovskite domain and a rod that is growing on the top, and we were really trying to figure out what is this material. We were struggling because from, for example, the Fourier transform of the lattice, you can identify that, okay, this is cesium lead bromide, and you have an idea that this rod is probably a mixed lead bismuth sulfide. But there are a lot of mixed bismuth sulfides, at least 5 phases, probably more. They can do alloys between each other, and they all look similar crystal structure-wise. So it's difficult to resolve which one of the two is or of the 6 actually is the real case. So here is where we resorted to our tool. First, we extracted some crystallographic information. I'm not going too deep into it, but from the analysis of these FFTs, you can learn basically something about the crystallographic orientation. You know the plane that the perovskite is exposing, you know the plane that the bismuth lead sulfide is exposing. After that, you notice that you have another epitaxial relation here. Basically, the planes are continuing each other at the interface, which is also important to discriminate between the options. And you can feed this information into the model to try and lower the possibility. So if you have no idea whatsoever of which material is this, you end up with 90 possible interfaces given these Miller indices. And each of them comes with about a dozen of models. So your complexity of the problem grows really, really quickly. But what we could do is that we could actually simulate all these 200 models on my laptop in a couple of hours. This is a remarkable result, because usually if you do it even with DFT on a supercomputer, it would take a while, but this potential is really fast. And when you rank all of them by energy, you have a clear winner. You have a structure that is lowest with respect to all the others. It's this structure here, 110 cesium lead bromide, 2100 galeno bismuthite. And when you go and check the crystal structure, you see that it's nicely connected. There is low strain. There are bonds forming in the interface. You overlap it to your initial experimental information, and it matches perfectly. You could not do it before, because there are so many models so similar among each other that if you don't have an energy evaluation that backs it up, it would be very difficult to tell if your prediction is correct. But with a model that backs it up, you can do it. And the nice thing is that this system is basically working for any kind of ionic semiconductor. Here are a few examples, not from the colloidal world, from the more traditional physical or chemical vapor deposition epitaxy. You see that we have sulfides, we have arsenides, a lot of oxides, mostly because oxides are very popular. And in all cases, our predictions match really, really well with the TM images. So the system is robust, reliable, and accessible. To conclude, one first move towards accessibility is that we transformed our code into an application that you can install on a laptop. This is directed mostly to colloidal synthesis chemists who maybe don't have this much of an expertise on coding, but they can benefit from like single spot simulation, like 2 materials, they put them together as they like, they see if the interface works, and they go in the lab, try to cook them, as we do. The next step will be, and we are working on that, but it's challenging, of course, you understand that, is to implement this kind of library that is a Python library, open source, to do a massive exploration of inorganic crystal structure databases and basically come up with epitaxy databases that are very quickly generated and doing models optimized. I think with this I have concluded. Yeah, I have concluded. So I want to thank, of course, Liberato Manna, the professor whose group I was working until like recently. I want to acknowledge the people at the Carnegie Mellon University, because it would have been impossible for us to code such a complex thing without their help. Of course, I want to thank IEMAP for funding. And I guess I also want to thank you for your attention. I hope there are questions, and I'm ready to take them.
Thank you, Stefano, for your very interesting presentation. Okay. Does anyone else have any questions? No. However, it's very useful, this code, because avoid a lot of work for researchers. Because I remember when I built a few years ago an interface between magnesium and magnesium hydride, and I had to explore all the possible, not all the possible, but a lot of possible stacking sequence. And
Exactly.
for each of them, DFT calculation, build the curve of the energy curve, the Uber curve. And it is a very big work. So
yeah, here the idea is to help people who cook, right? To provide the fast feedback. It of course is not as accurate as DFT. We don't have this ambition. But the nice thing is that you get close enough to the minimum, to the energy minimum, that then
you can explore
exactly
around
you feed it to DFT, and it's much faster as well, right? The big challenge we have now is that we want to implement metals, because at the moment it works only with ionic systems, and that's a big bit of a limitation, because you want to have metals in that. We are developing the potential for metals, but it's not ready yet. So it is kind of working. I would say 80% of the times is working, but we are not happy yet. So we're trying to make it better.
Okay, thank you again.
Thank you.
And now let's. Oh no, there is a question from
okay.
I think, from Gabriele.
Could you comment more on the potential for metals? What do you aim to do for the future to include metals?
Yeah, okay. My realistic plan for the future is to call Derek, who's the guy who codes, and ask him please to implement the metal. No, but no, in reality, so the potential that we are exploring is based on electronegativity differences. And plus, I think it has some pre-built knowledge on the bonding distance. So basically, I think what I am much more familiar with the electrostatic potential, but what I think the metal potential is doing is that it tries to optimize the lateral position of the metal domain based on electronegativity differences between atoms. So it tries to recover as much as ionicity you can find at the interface. And then it uses the bonding distances to make sure that you do not collapse the two domains on each other. I'm not completely sure. It does work quite nicely for the geometry optimization. So when you feed the material inside, the geometry is very reasonable, it's sound. But I think the problem is that the energy evaluation becomes less reliable than compared to an electrostatic potential. Because here you have like sort of a formal, Coulomb electrostatic interaction equation that you can use, and in that case, it's not as trivial. But I think you have to wait for the follow-ups to know more, because I don't know myself exactly.
Okay, thank you. That's interesting. It's still electrostatic, basically, because there's not much you can do otherwise. But that's an interesting future development. We are looking forward.
Thank you.
Okay, thank you, Stefan, again. And now let's leave the floor to Juliette Zito.
Hi.
Good morning, Juliette. And okay, try to share your presentation. It's okay. We see.
Yay.
If it's possible in full screen mode.
Yes, I'm trying to wait a second. Okay, now I think
okay,
you have
perfect.
the full screen.
Yes.
Okay.
Yes. Thank you. Please.
Perfect. So, hello everybody. Today I will show you how we can use computational chemistry for studying quantum dots. So, first of all, what computational chemistry am I talking about? So here in this talk, I'm referring to atomistic computational methodologies, and in particular to first principle calculations. And these imply to solve the Schrödinger equation, to have information about the position of the atoms in the systems that you are studying. And solving these equations enable us to obtain both structural but also electronic information about our systems, because we are solving quantum equations. So these are very accurate methodologies, but they also come at a high computational cost. But on the positive side, with the recent developments in computing power that also Simone was pointing out this morning, and the development of more and more powerful and efficient supercomputers, it is nowadays possible to employ these first principle simulations to model complex systems such as quantum dots. So these quantum dots, I think all of you heard about them. So last year, Bawendi, Bruce, and Yakimov won the Nobel Prize in Chemistry for their discovery and synthesis. And they possess a variety of very fascinating quantum properties. And maybe the most notable is the fact that by varying their size, you can tune their band gap. And this makes them particularly useful for applications in photovoltaics, bioimaging, and optoelectronics, for example. So here just a quick overview of the structure or the components of quantum dots. So they are made of a core of a semiconductor material of nanometric dimension. This is the photoactive part of our materials. And this core is capped by an external shell of organic ligands, which are basically surfactants, that keep them colloidally stable in organic solvents that are employed. And as for the core, you have a variety of possible materials, and the families range from metal chalcogenides to metal pnicogenides or perovskites. So one of the main challenges for quantum dots is that a very high fraction of their atoms are located at the surface. So if you take a typical cadmium telluride quantum dot core of about 4.2 nanometer in diameter, you can see that more than 30% of the cadmium atoms are located at the surface. And defects can arise on this surface that can lead to the formation of these mid-gap states, which in turn can act as traps for the charge carriers, therefore reducing the photoluminescence, but also the charge transport properties of our quantum dots. So the two questions that arise here are: what exactly are these defects, and how can we heal them? And to answer these questions, we have developed in the framework of IEMAP an integrated experimental and computational workflow. And today I will guide you through the computational part, let's say. So everything starts with building a realistic quantum dot model in order to understand and describe in atomistic detail the surface of your quantum dot. So this is already a challenging step because unlike organic molecules or bulk materials where you do have a fixed stoichiometry of your system, so for example, in this molecule, you know that you have 8 carbon atoms and 16 hydrogen atoms. In the case of quantum dots, you have variable stoichiometries. Also, you have variables, shapes and faceting, and you don't know where are the ligands, how many are there, etc. So to build a realistic quantum dot model really requires a synergy between experiments and simulations. And the very first step when you want to build a model is to look at the size, shape, and faceting. So for instance, if we take the case of this perovskite material made of cesium, lead, and a halide, that can be chloride, bromide, or iodide, from experimental analysis, and in particular transmission electron microscopy, you know that in most of the cases, these perovskite quantum dots have a cubic shape, exposing these 001 facets here. And you can also get some information about the size of the particle and the size distribution. So now from the computational point of view, once we collect this information, we start from the bulk structure of the perovskite, in this case, the cubic lattice. And we will use this online tool called Nanocrystal Builder to cleave the bulk with the correct size, the correct faceting, and the correct shape. However, when we cut a cubic bulk, we can end up either with a model that has this cesium halide termination, and in this case, the anion to lead ratio is higher than the one in the bulk, so higher than 3, or you can end up with a lead halide termination, and in this case, you have a lower anion to lead ratio with respect to the bulk. So to select the correct model, we will look at the typical experimental diameter, and by comparing with experimental analysis such as ICP or XPS analysis, we will select the model with a high anion to lead ratio, that is, this cesium halide terminated model. However, in our simulations for the size, we will select a lower size with respect to the experiments to reduce the computational load, because we will then use first principle methodologies that are computationally demanding. However, we have a nanocrystal model with the correct shape and surface termination. Now there is a last thing to check in our model, and this is if our model is charge balanced. This means that if we take the cesium in its more stable oxidation state of +1, the lead in oxidation state +2, and the bromide -1, in the model as cut from the bulk, we obtain an excess of positive charge that has to be balanced by removing 8 positive charges, and in this case, 8 cesium ions from the surface. And here we end up with a charge balanced system and with our final quantum dot model that can be written as made of an inorganic stoichiometric core with an inner shell, surface shell, which is still inorganic, and then an outer surface shell, which in our model is inorganic, so A is cesium and X is bromide. But in the experiments, A can be a cationic ligand, such as ammonium ligands, and X can be anionic ligands, such as olate ligands, for example. And with this same methodology, over the years, let's say, our group built up several types of quantum dot materials. The most recent are indium phosphide quantum dots. And in the framework of IEMAP, what we did is to prepare some automated tools that enable to only give as input parameter the diameter of the nanoquantum dot that we want to model, the crystallographic information about the bulk structure we want to use, and the shape that we want to achieve. And this script will automatically prepare for you the quantum dot model and also charge balance and do everything automatically. And this is obviously very useful for us as computationalists, but it can also be used for experimentalists to have at least an initial visualization of the atomistic structure of the quantum dots they are preparing. So now the next step, once we have an atomistic understanding of the surface, is to identify the origin of trap states. And in particular, the relationship with the coordination number and the type of ligand binding at the surface. So for our perovskite quantum dot, starting from here, we can investigate how the surface is can be degraded by progressive loss of this external and this more internal external outer shell. And by employing first principle simulation, we can systematically study not only the role of this loss of external shell on the structure, but also on the electronic properties of our quantum dot model. And with this type of simulations, we found out that in both cases, there is the formation of mid-gap trap states above the valence band, and that these states arise from a reduced coordination number of the lead atoms, and result in the formation of these very localized and detrimental trap states. And more recently, we did the same type of investigation also on indium phosphide quantum dots, and we again systematically modeled the loss of Z-type ligands from the surface. So in our models, these ligands were indium chloride 3 units, either from the corner, the edges, or the surface, the center of the facets. And here again, we found out that a reduced coordination of, for example, the surface phosphorus always gave rise to the formation of these deep hole trap states, while a reduced coordination of the indium atoms at the surface gave rise to electron traps. So these materials were found to be much more sensitive to the formation of trap states than the, let's say, well-known cadmium selenide quantum dots. But now let's come to the final step. So once we have identified the origin of trap states, we also need to design optimization strategies. So the most, let's say, obvious optimization strategy, since we saw that most of trap states arise from a detachment of ligands, is to design a stable shell of organic ligands. So for example, for our perovskite, we saw that the traps were arising from the detachment of both the external and internal surface shells. So for recovering the optical properties of perovskite quantum dots, the computational work proposed to add lead bromide salts and also add more stable ligand shell. So by replacing this cesium here, for example, by a quaternary ammonium organic ligand. And in the experiments, this led to the boosting of the photoluminescence quantum yields to next to unity. And most importantly, that was retained even after several rounds of washing. But more recently, in the context of the IEMAP project, we are investigating another type of strategy to passivate these surface defects, which is to interface our material, in this case the perovskite, with another inorganic material. So as also Toso anticipated, we have investigated how to interface chloride-based perovskite with a lead sulfide. And in the experiments, they found out that these systems have a heterodimer structure represented here. And what we can do from a computational point of view is to investigate again the structure and the electronic properties of these new materials. And structurally, we found out that there is this stair-like epitaxial alignment between the two materials that enables to complete the coordination of the lead atoms, both from the perovskite part and from the lead sulfide part. So basically, the interfacing the two materials was healing the defects in both domains. And from an electronical point of view, when we are looking at these interfaced materials, a very important concept to look at is the band alignment between the two materials, because we are looking at two semiconductors. And in this case, we found out that the lead sulfide material, here in red in the plot, was dominating both the conduction band edge and the valence band edge. So with a type 1 band alignment between the two semiconductors. So actually, the emission in this system was not coming from the perovskite, but rather from the lead sulfide. But this emission was still very efficient because of this favorable epitaxial alignment that allowed to heal the surface defects of both sides. And again, in the context of the IEMAP platform, another material that was studied, as also Luca described very intensively before, is to grow an inorganic material shell around 3,5 semiconductors, in particular indium arsenide. So we saw before that these type of materials are very sensitive to the formation of trap states upon detachment of Z-type ligands. So a good strategy to avoid this detachment of ligands is to grow an external shell of inorganic material around this indium arsenide core. And experimentally, doing so was found to boost the photoluminescence of the indium arsenide from 10 to above 40%. And again, using first principle simulations, it is possible to investigate the newly core shell material that is formed, and to investigate in particular the interface, which is a very delicate part where strain can arise. And here it was found that there is an interlayer of indium, zinc, selenide, and cation vacancies between these to core and shell parts that is very favorable. And from an electrical point of view, this core shell material again results in a type 1 band alignment, where now both the electron and wave function are localized inside the indium arsenide core. So this allows to confine the charge carriers inside the core and to promote the radiative recombination of the carriers, resulting in these increased photoluminescence quantum yields. So to conclude, I hope that I have convinced you that quantum dots are very promising materials for optoelectronic devices, but they suffer of efficiency losses due to the presence of surface defects, and that computational chemistry is a powerful tool to identify the origin of these trap states and understand in detail the surface, and that together with experiments, computational chemistry can lead to major improvement in these materials. I thank you for your attention, and I thank Professor Liberato Manna, which is supervising me, all the computational team that is now quite scattered around Europe, and also Massimo Cellino and Simone Giusepponi for taking care of the supervision and of the computational part of this project.
Thank you, Juliette, for your very interesting presentation that ends the second session of the morning.